Alright, this is homework 3.2. This problem set is pretty heavy on math, so I won't be going over literally every single calculation, just the concepts that you need to know to do them. So, for the first one, if 42 kilojoules of heat is added to a 32-gram sample of liquid methane under 1 atmosphere of pressure at a temperature of negative 170 degrees Celsius, what are the final state and temperature of the methane once the system equilibrates? Assume no heat is lost to surroundings, and then it gives the normal boiling point and the specific heats of liquid and gaseous methane. So the first thing we're going to do before we find the overall temperature is find the amount of energy it takes to convert from a liquid to a gas, going from negative 170 degrees Celsius to negative 161.5 degrees Celsius. So first of all, we find the change in temperature that we need, 8.5 degrees up here. And then we go in with our specific heat and calculate the amount of energy it takes up here. And you just solve it, use your unit canceling, grams cancel out, Kelvin cancel out, and you're left with 0.95 kilojoules. And then you can't just use your specific heat, you also have to use your enthalpy of vaporization, very important, which is 8.2 kilojoules per mole. And then since we don't have moles, we convert grams of CH4 or methane to moles of methane, and it's pretty nicely split into 2 moles. And then we use that for our calculation, 8.2 kilojoules per mole times 2 moles, moles cancel out, and we have 16.4 kilojoules. And then we add those two values up, and we have 17.3 kilojoules. And that gives us the amount of energy that's needed to convert from a liquid to a gas, and then we can use the rest of that energy to find the change in temperature. And that's what I will do next. And then after we get our energy, we just subtract our total energy from energy to convert or transition. So we do 42 minus 17.3, and we get 24.7 kilojoules left. And then we go in and calculate our energy using our specific heat of gaseous methane, which is 2.22. And then we just go, and then my thought process was going from kilojoules to joules, and then converting using the specific heat right here. And then, cancel the units, and we get 347 degrees Celsius, or just 347 degrees in general. And then finally, we just calculate our change in temperature by doing negative 161.5 degrees Celsius, which, by the way, is our temperature after our phase change, plus 347 degrees Celsius, and we get to 185 degrees Celsius, and that is our final answer. Alright, after that incredibly long problem, we got some easier ones. So, 6, propanol and ethyl methyl ether have the same molecular formula but different normal boiling points. Please explain why and rationalize the difference. So, propanol benefits by having an OH, or hydrogen bonding, which greatly increases its intermolecular forces, while ethyl methyl ether doesn't. It just has a CO bond, which doesn't mean anything, it's just there. So, propanol will have a higher boiling point because it has much stronger intermolecular forces because it has those stronger hydrogen bonding. And then for 7, we're given a phase diagram and are asked to estimate the normal boiling point, freezing point, along with some other stuff. So, looking at the phase diagram, we know that the blue is solid, the little lighter blue part is liquid, and the yellowish tannish part is a gas, or the gaseous state. So, we know that this blue line is the freezing / melting curve. The rightmost line is the condensation / boiling curve. And this is like the sublimation curve. So when we want to estimate the normal boiling point, the normal freezing point, we have to find it at 1 atm because standard temperature and pressure is 1 atm and 270 degrees Celsius. So standard pressure would be 1. So when we want to find the normal boiling point, we would find 1 atm on this red line and find where it is. It's like 350, 360, something like that. So I would say it's 360 Kelvin. And then for solid to liquid, I would say it's like, again, we're looking at 1 atm. It's like 250, 260, 240, around that area, like mid 200s. And that is our answer for A. So for B, it's asking for the physical state of the substance under the following conditions. So for 1, we're given 150 Kelvin and 0.2 atmospheres, and that would land kind of neatly in gas. And then for 2, 100 Kelvin, 0.8 atmosphere, that would be in like solids. Yeah, like here. And then last one, 300 Kelvin and 1 atmosphere, that would be a liquid. What is the triple point? The triple point is when all 3 phases meet, or when all of the things meet. It'd be right here, like when all of the lines meet. So I would say that it would be like approximately like 180 or 170 at like half, like 0.4 ATM. So yeah, that's that on those two. So 26 and 28, these are kind of like the same question. Rationalize the difference in boiling points between each pair. So for A, we have HF and HCl. HF has a higher boiling point because it benefits from having hydrogen bonding, where fluorine is the most electronegative element on the periodic table, so it qualifies as having hydrogen bonding along with nitrogen, oxygen, and fluorine. So that's why on A. For B, CHCl3 and CHBr3. Bromine is a much larger atom than chlorine, so it has much stronger LDF forces, so that's why it has a much higher boiling point. And then for C, uh, bromine and ICl. ICl is a polar molecule, so it's going to have those dipole-dipole forces that will increase its boiling point rather than bromine's just dispersion forces. So that's why ICl has a much higher boiling point. And then for 28, it asks to identify the types of intermolecular forces present, and then select the substance in each pair that has the higher boiling point. So for A, we have propane, which is on the left, and N-butane, which is on the right. So propane is smaller overall, and butane is larger overall. And since they are both nonpolar and have no hydrogen bonding, it is just LDF forces. So that is why butane it has a higher boiling point because it is larger. And then for B, diethyl ether and butanol. So butanol benefits from having an OH group, which gives it hydrogen bonding, which greatly increases boiling point, while diethyl ether just has this weird bird shape, and although it is I think is polar, it does not beat out butanol's hydrogen bonding, so that's why butanol has a higher boiling point. And then with SO2 and SO3, SO2 is smaller overall than SO3, so SO3 has greater molecular weight, therefore SO3 has the higher boiling point. And then finally with D, phosgene and formaldehyde, phosphene's on the left, formaldehyde on the right, they have the same molecular structure, except phosgene has 2 Cl atoms and formaldehyde has 2 hydrogen atoms. So since phosgene has 2 chlorine atoms, which are larger, much larger overall, it will have the higher boiling point. So it is going to be SO3 and that. So that's that on those two problems. All right, 40 and 41. Name the phase transition in each of the following situations and indicate whether it is exothermic or endothermic. So exothermic means it's releasing energy, and endothermic means it's taking in energy. So bromine vapor, and this is part A, bromine vapor turns to bromine liquid as it is cooled. So vapor turning to liquid, that means it's condensating, and that's exothermic because it needs to be cooler as heat is being released. And then for B, crystal iodine disappear from an evaporating dish as they stand in a fume hood, so it's going from a solid to a gas. So that's sublimation, and that takes energy, so it's going to be endothermic because it takes energy to do that. And then C, rubbing alcohol in an open container slowly disappears. That's going to be vaporization or evaporation, and that takes energy to do, so it's going to be endothermic. And then finally for D, molten lava from a volcano turns to a solid rock. That's going to be freezing, molten to solid, and that's going to be exothermic because energy is being released. Energy is releasing from the molten lava so that it can solidify. So, 41. Explain why any substance heat of fusion is generally slower than its heat of vaporization. So, when we have a substance going from a solid to a liquid, like this, and it's a structured form, when you're going from a solid to a liquid, generally you're just breaking that structure and it becomes like a liquid, while they are still like connected together. So it takes less energy to do so. Like it takes energy, but not that much as when you're going from a liquid to a gas where you are literally breaking up every single intermolecular force so that they are completely separate from each other. Because when you're going from a solid to a liquid, you still have those forces connect them together. It's just less structure. But when you're going from a liquid to gas, you're losing that structure entirely, and you're losing that force entirely. There is nothing, well, basically nothing, keeping them together. So that is why the energy requirement is much higher.